Hello everybody. Welcome to video lecture on Introduction to Pushdown Automata, Equivalence of Pushdown Automata and Context-Free Grammar in Theory of Computation. The agenda for today's topic is Pushdown Automata, Equivalence of PDA and CFG, Conversion of CFG to PDA, Conversion of PDA to CFG. Let us see in details.
We've seen that finite automata give rise to the class of regular languages. Finite automata have no memory except for the current state, and they have only a finite number of states. So finite automata cannot accept languages like a to the n, b to the n, where you need some kind of counting to make sure that there's as many a's as b's. So our next goal is to find a class of automata that corresponds to the context-free languages, so that can accept languages like a to the n, b to the n. And the idea is to equip automata with a stack. And the stack has an unlimited size, so it can be used to perform things like counting. So next to our input alphabet sigma, the automata now also have a stack alphabet gamma. And what's a stack? A stack is just as you imagine, you stack things on top of each other. And the crucial property of a stack is that you can only add and remove elements from the top of a stack. So we can add things on top and remove from the top. For instance, we could remove the D here, but we cannot remove the A from the bottom. We will write stacks as words, and we will write them with the topmost element on the left. So this stack ABCD would be written as DCBA. D is the topmost element, A is the bottom element on the right. Now our pushdown automata that work with a stack, they are basically an extension of non-deterministic finite automata. They also take in the transition function the state as an input of the transition function, the input letter or a lambda transition. So this part is just the same as for non-deterministic finite automata, but the transition function additionally inspects the topmost element on the stack. And now the transition function gives us as result a possible choice of states to switch to and a word over the stack alphabet. That's the new elements that we add on top of the stack. The element that we inspect on the stack gets removed, and the elements that are given here are added back on top of the stack. So it switches the state and it adds 0 or more elements on top of the stack.
Be looking at this problem, which is very interesting in that there's a very simple procedure to do it, and a lot of students ask me about how to actually do this. So let's go into this. So we have a CFG given right here, given by these two variables s and b, and we want to convert it into a PDA. So how do we actually do that? Well, remember a PDA has a stack, and what we need to do is to utilize the stack by applying the rules on the stack. So if a terminal is on the top of the stack, we want to read it off of the input at the same time as popping it. And if there's a variable on top of the stack, then we're going to apply a rule corresponding to that variable. And to make sure that the computation finishes correctly, we always will put a bottom of stack marker so that we never pop an empty stack. So what we should do then is, in the start state, we're going to not read anything. So most of these transitions will not read anything other than ones that we'll see, a few that we'll see later. So we're not going to pop anything because we shouldn't pop when there's empty stack. And we're going to put a $sign on the bottom. Well, really any bottom of stack marker, a special character is fine. So then we come to here, and then now what we're going to do is to start the derivation, because we want to simulate the derivation on the stack. Well, every derivation starts with the start variable. Well, the start variable in this grammar is s. So we're going to put s on the bottom of the stack Again, not reading anything. So, and not popping anything because I don't want to pop the $ that we just put on. So now we're going to come to a state I call Q loop. And the whole goal of this state is to assess what's at the top of the stack and decide what to do from there. So if a variable's on top of the stack, then apply a rule. If a terminal's on top of the stack, read off the input at the same time as popping that character off. And if a $sign's on top of the stack, go to a final state, which means that you should accept at that point. So let's handle the terminals. So what are the terminals in this grammar? Well, it's everything that's lowercase, A, B, and C. So we're going to have 3 self loops right here. So this will always happen for every terminal in the grammar, no matter what. So then here we're going to have A, because we're reading off the input, always popping the same character and then pushing nothing. So as the characters are being produced on top of the stack, they'll never change because we have a context-free grammar. In the derivation, once you make a terminal, you'll never change it. So here, what we're trying to do is we're trying to match off of the input at the same time that they're being produced on the stack. So then we're going to do exactly the same thing for the B terminal and the same thing for the C terminal. No problem. If we have a $sign on top of the stack, we need to go to an accept at some point. So I'm going to have epsilon $sign goes to epsilon, go to a final state. And these 4 states right here, these 4 states, I'm going to call the base states. So these 4 states will always be there, always, regardless of what the CFG looks like. It'll always be there. But now we need to handle the rules. So what we need to do is to make a series of transitions that go out from Q loop and then eventually come back to Q loop. And what we're doing is we're going to pop a variable off the stack and then push on the right-hand side of one of its rules. So for example, if we are doing the rule S goes to ABC, then if an S is at the top of the stack, then eventually when we come back to Q loop, we want to have A, B, C on top of the stack. So where A, the terminal A in this case, is at the top, which means that we need to push on the right-hand side of the rule first. We need to push the C on first, then the B, then the A, because of how a stack works. A stack needs to have its last thing on the top. And we want the A on the top, so we want to push it last. So let's handle S goes to ABC. How we're going to do that? Well, what we're going to do is we're, again, not going to read anything. So the only transitions that read are these ones right here. So maybe we'll mark this here. So these are the only transitions that read. Because in all other cases, we're going to be applying a rule, and the only time that we're going to be consuming characters is when a terminal is produced, which means that they're at the top of the stack, which means these are the only ones that are going to read anything. So this one doesn't read. Here we got to be able to pop an S off in order to be able to apply this rule. And what I'm going to do here to save space is I'm going to push the C on immediately because we have to push the C on first. Then we need to push on the next thing after the C, actually I guess before the C, which is the B in this case. So epsilon, because we're not popping anything, goes to B. And then when we'll come back with the last thing, which happens to be an A in this case. So epsilon goes to A. And we'll do this exact same procedure for every rule in the grammar. So we did S goes to ABC. Now let's do S goes to a, little b. So what I'm going to do is have another set of transitions that go out and come back. So epsilon s goes to b because we have to push the b on first since it's last. And then we got to push the a on first. I mean next. And go back to Q loop for that reason. 2 more to go. Let's do B goes to SB. So then here, I'm going to have, again, epsilon, no read. We got to pop off the variable on the left side of the rule, which is B in this case. And then we're going to push on the rightmost thing in the rule, which happens to be B. So effectively, this rule does nothing, except we can only take it if the B appears at the top of the stack. So then we come to a state, and let me squeeze this in here. So this will be epsilon goes to S, and then finally I'm going to squeeze in a self loop right here, because for the epsilon rule we can just do it in one transition instead of two. So here we're going to have epsilon B, because again we want to apply this rule and we can only do it if the thing that is on the top of the stack is a B. And we don't want to push anything because there's nothing on the right hand side. And there we go. So the thing to take home from this is the 4 base states are always going to be the same. You're always going to push on a special character, then the start variable, go to a state called Q loop, and then you're going to have epsilon, the special symbol goes to epsilon to a final state. The Q loop state always has self loops on every terminal, and you will always have one of these types of transitions where it always comes out, comes back for every rule in the grammar. So we should say for each rule in the CFG. For each rule in the CFG, we're going to make a series of transitions like this that go out from Q loop and then eventually come back. And that is how to convert any CFG into a PDA.
In this class we discussed about push-down automata, equivalence of PDA and CFG, conversion of CFG to PDA, conversion of PDA to CFG. Thank you.